Creating mini-stars inside reactors like this is one of the greatest technological challenges humanity has ever faced.
3, 2, 1.
Japan just admitted they've created something so powerful, it's terrifying.
These results are really significant because what we've managed to demonstrate inside JET is that we can create a mini sun, the right kind of mini sun, hold it there for a sustained period and get really good performance levels.
A machine so powerful it could change how we use energy, but also so risky that one mistake could cause a disaster. This isn't a scene from a movie. It's happening in Japan right now. The JT60SA fusion reactor can heat things up to 200 million degrees Celsius, making it a huge scientific achievement. But what if something goes wrong? What if this incredible machine becomes a ticking time bomb? But before we get too comfortable with this scientific marvel, let's confront a scary thought. Could this reactor go from being our hope to becoming a threat? Inside Japan's JT60SA fusion reactor, now let's explore the heart of this powerful machine and the serious risks that come with controlling such extreme energy. The JT60SA, often called the fusion frontier, uses the latest technology to keep everything running smoothly. But what happens if something goes wrong? With its 18 giant magnets and a core cooled by liquid helium, this reactor needs to work perfectly. A single mistake could lead to a disaster worse than we can imagine. Stick with us as we uncover the shocking truth about the JT60SA's potential and why some experts are worried it might be more dangerous than we think. But the story doesn't end here. This fusion reactor also plays a key role in long-term research, pushing the limits of today's fusion technology and paving the way for future discoveries. As a leader in the global effort to harness fusion energy, the same energy that powers the sun, this facility in Japan is more than just a reactor. It's a lab for the future of energy, focusing heavily on plasma control experiments. These experiments are vital because they teach scientists how to keep the plasma stable inside the reactor, a critical challenge in making fusion energy a reality. The project is a major collaboration between the European Union and Japan aimed at advancing global fusion energy research, particularly to support the ITER project. Launched in 2007 and completed in 2020, JT60SA is an advanced tokamak fusion device designed to tackle key challenges in achieving efficient and sustainable fusion energy. With a heating capacity of up to 41 megawatt and superconducting magnets, is built to confine high-temperature plasmas for extended periods, up to 100 seconds. This is crucial for studying the high-density plasma conditions needed for ITER. The facility's advanced plasma diagnostics and enhanced confinement capabilities support studies on managing power and particles under intense heat. These studies are key to understanding and optimizing the conditions necessary to reach the break-even point, where fusion produces as much energy as it consumes. Additionally, it is essential in the development of future fusion power plants. It investigates steady-state operations and different diverter configurations, which are crucial for the practical use of fusion energy. The facility also includes a remote handling system for in-vessel maintenance, showing a design that considers long-term operational needs and safety. Organizing a complex project like this is a huge task, but it's essential for bringing together a strong team of researchers and engineers. This growing group is key to keeping and expanding the knowledge needed for future fusion energy projects. In Japan, the cutting-edge fusion reactor uses powerful magnets to contain super-hot gas, known as plasma, within a donut-shaped chamber. This incredible technology, which is the largest and most advanced of its kind in the world, plays a key role in the International Thermonuclear Experimental Reactor, ITER project in France. It's helping scientists unlock the mysteries of fusion energy. After nearly 15 years of careful development and testing, JT60SA made a big leap by creating its first plasma. This major achievement proves that the reactor works as intended. Sam Davis, the project manager at Fusion for Energy, confirmed that everything is running smoothly. Fusion for Energy, a European Union organization, works closely with Japan's National Institutes for Quantum Science and Technology to keep track of and assess the reactor's progress. At the heart of the reactor's work is nuclear fusion, where two smaller atomic nuclei combine to form a larger one, releasing a massive amount of energy. This happens in a special state of matter called plasma, which is extremely hot and filled with charged particles. Mastering this process isn't just a scientific win, it could lead to an almost endless supply of energy, similar to how the sun produces power. But this wasn't the toughest part. Even though they succeeded in creating plasma, scientists still face many challenges in controlling and maintaining such a powerful reaction. There's still a long way to go, but the progress so far marks a huge step forward. Plasma is a unique state of matter, different from solids, liquids, and gases. It consists of free-moving electrons and positive ions. This extraordinary substance powers the sun and all other stars. In the sun's core, atomic nuclei collide at incredibly high temperatures, about 10 million degrees Celsius. These extreme temperatures give the nuclei enough energy to overcome their natural repulsion and fuse together. Fusion happens because, at close distances, the nuclear force is stronger than the repulsive force. For fusion to occur, the nuclei need to be packed tightly together to increase the chances of collisions. The sun naturally achieves this with its immense pressure and gravity. But why is fusion energy so captivating? The interest in fusion began in 1925 when British scientist Arthur Eddington proposed that stars like our sun get their energy from nuclear fusion, where hydrogen nuclei combine to form helium. But this wasn't the final word. Scientists continue to study and experiment, trying to harness the power of fusion energy on Earth. The path is full of challenges, but each step brings us closer to unlocking a new, powerful source of energy. Join us in the following chapter as we delve deeper into the scientific breakthroughs emerging from this pioneering research. Overcoming challenges for future energy. Driven by the forces of nature, scientists have been working tirelessly to harness this powerful reaction and unlock vast energy reserves. Since the mid-1900s, the idea of fusion has captured the attention of many. A fusion power plant would produce much less radioactive waste compared to traditional nuclear power plants, which generate energy by splitting uranium atoms. But even this isn't the biggest challenge. Let's delve deeper into the science that aims to turn fusion from a concept into reality. Just 1 gram of hydrogen isotopes, the fuel for fusion, could produce as much energy as nearly 10,000 kilograms of coal. Once scientists understood the principles of nuclear fusion, they became dedicated to mimicking and controlling this powerful reaction. If they succeed, nuclear fusion could provide a limitless, sustainable, and clean energy source that could meet global energy needs. However, mastering fusion on a large scale is a daunting task. Bringing fusion energy to Earth is no easy feat, but the potential benefits are enormous. Fusion could produce 4 times more energy per kilogram than the nuclear fission processes used in today's reactors. This huge difference drives scientists worldwide to keep pushing forward, striving to make fusion a practical energy solution. But the road ahead is still long and filled with challenges. Imagine an energy source about 4 million times more powerful than burning traditional fuels like coal or oil. Most modern fusion research focuses on using tritium and deuterium, 2 forms of hydrogen with extra neutrons. In theory, just a small amount of this fusion fuel could power a large country for 5 years. But this wasn't the biggest surprise. Fusion fuel is not only incredibly powerful, but it's also relatively easy to find. Tritium can be made when neutrons from fusion reactions hit lithium, an element that is plentiful on Earth. Deuterium can be easily extracted from seawater. These resources could last for countless generations, and unlike conventional nuclear power, fusion doesn't create long-lasting radioactive waste that could harm the environment and our health. What's truly remarkable is how future fusion reactors are designed with safety in mind. They are built to operate under strict conditions, so if something goes wrong, the fusion process would just stop. The plasma needed for the reaction would safely dissipate, making fusion power a major step forward in the quest for clean, reliable, and safe energy. Fusion consumes its fuel quickly, which prevents any long-term damage to the reactor itself. This fast consumption ensures there's no risk of an out-of-control reaction or catastrophic meltdown. Unlike other nuclear processes, starting and maintaining a fusion reaction is incredibly difficult. Even so, both nuclear fusion and fission help the environment by not producing greenhouse gases. Looking ahead, nuclear fusion holds the potential to become a dependable source of low-carbon power. But this wasn't the end of the challenge. While the sun's immense gravitational forces naturally make fusion possible, replicating this process on Earth is much more complex. To start fusion using deuterium and tritium, temperatures must soar above 100 million degrees Celsius. However, reaching these extreme temperatures is just one part of the challenge. Controlling magnetic forces and maintaining precise pressure levels are essential to keep the plasma stable and sustain the fusion reaction long enough to produce more energy than it consumes. Current experiments are getting closer to these critical conditions, but there are still major obstacles, like improving energy containment and plasma stability, that need to be overcome before nuclear fusion can become a practical reality. Maintaining and achieving the extreme conditions required for nuclear fusion is no easy task. It's incredibly difficult and expensive, but scientists around the world are committed to making it happen. They're working tirelessly to find practical solutions, even though it's a slow and challenging process. The potential benefits, however, are enormous. Nuclear fusion could provide a nearly endless supply of clean energy, which could completely change how we power our world. Around the globe, teams of scientists and engineers are trying out new materials and designing complex systems to achieve net fusion energy. Over 50 countries are involved in this effort, making significant progress in nuclear fusion and plasma physics. Recently, there was a breakthrough when, for the first time, a fusion experiment produced more energy than it consumed. This success was thanks to advanced technologies like magnet-based fusion devices such as tokamaks and stellarators, along with the use of special fuels, lasers, and other cutting-edge tools. But even though this was a huge step forward, the journey is far from over. The speed at which the fusion industry can develop and prove these new technologies is crucial. Success depends not only on technological advancements, but also on securing enough resources through global partnerships. Building a strong nuclear infrastructure with clear standards and best practices is essential if we want to bring this new energy source into everyday use. One of the leading projects in this field is Japan's reactor is designed to heat plasma to an incredible 200 million degrees Celsius and keep it that way for about 100 seconds. These extreme conditions allow scientists to study and improve plasma performance, which is vital for making fusion power a reality. This reactor is supporting ITER, a massive international fusion reactor being built in France, which aims to show that fusion power can actually produce more energy than it uses, and it relies heavily on the knowledge gained from experiments like those at JT60SA. Japan was given the opportunity to build the JT60SA and 2 smaller fusion facilities in exchange for France hosting ITER. This arrangement was part of a broader agreement between the EU and Japan in 2017, which also included upgrading Japan's older JT6 reactor, which has been in operation since the 1980s. This global initiative highlights the shared commitment to revolutionizing energy production through fusion, paving the way for a new era in how we generate power. With these developments in mind, the next chapter will delve into the international collaborations and technological milestones propelling us toward a fusion-powered future. Race to unlock clean energy. The progress being made in these projects represents a major step toward cleaner and more efficient energy solutions. The whole world is watching, hoping that fusion energy will soon become a practical reality. This spirit of international collaboration shows how important it is for countries to work together to tackle global challenges and develop innovative energy solutions. Back in the mid-1980s, a major overhaul of Japan's JT-60 reactor began, leading to the creation of a much smaller yet highly advanced version called JT-60SA, or Super Advanced One. Despite its smaller size, holding only about half the height of ITER reactor, it can contain up to 135 cubic meters of plasma, which is roughly 1/6 of the capacity of that reactor. Alberto L., who heads the science division at that reactor, has noted how valuable the data from JT-60SA's experiments will be for further improvements. But the journey wasn't smooth. Unexpected challenges delayed the completion of the reactor by more than 15 years, beyond the original 2016 target. The team faced several challenges, especially when it came to getting the materials they needed. This shortage forced them to redesign the reactor to make sure it could survive the powerful Tohoku earthquake in March 2011. Fast forward to March 2021, during routine tests, they ran into another major problem: a short circuit in the cable connected to one of the superconducting magnetic coils. This short circuit disrupted the electrical system and caused a helium leak, making the project even more difficult to manage. The leak happened at a particularly tense moment, almost putting the cooling systems in jeopardy. This occurred when the electrical current was at its lowest, which was a lucky break. The project manager, Host Shiri from QST, explained how serious the situation was. He pointed out that if the electrical current had been stronger at that moment, the damage to the coil could have been disastrous. The JT-60SA team felt relieved that things didn't get worse. They were reminded once again of the constant ups and downs in the challenging field of fusion technology. After this incident, the team spent 2.5 years improving the insulation on more than 100 electrical connections to enhance safety. This problem led the developers at ITA to start more thorough testing on their coils to prevent similar issues in the future. But the JT-60SA still has a lingering issue. It only works with hydrogen and its isotope deuterium, not tritium. This limitation reduces its effectiveness in certain chemical reactions and restricts its broader application. The difficulties and compromises involved in creating such advanced technologies are clear. Tritium, a powerful form of hydrogen, is more expensive, harder to find, and more radioactive than regular hydrogen. Yet, it plays a crucial role in generating electricity through fusion, a technology that could change the energy landscape. The International Thermonuclear Experimental Reactor, ITER, plans to use tritium by 2035 to tap into this new energy source. Japan is determined to be a leader in the fusion energy sector, with a goal to have a working fusion power plant called DEMO by 2050. This plant would take the leap from experimental projects like JT-60SA and ITER to actual commercial fusion power generation. DEMO's main goal is to prove it can consistently produce net electricity from fusion, which would be a huge step towards sustainable energy. But this isn't the hardest part. DEMO also aims to be one of the first plants in the world to maintain stable fusion plasma for long periods and effectively manage the fuel cycle, especially when it comes to handling tritium. Tackling these challenges is crucial to showing that fusion energy can work on a large scale. Even though it's smaller, it plays a key role, similar to ITER, in developing the technologies needed for DEMO. Despite delays caused by natural disasters and technical problems, JT-60SA remains essential to Japan's ambitions in fusion research. Japan's vision doesn't stop with experimental reactors. The government has launched the Fusion Energy Innovation Strategy to boost Japan's role in global projects like ITER and to build the industrial skills necessary to manufacture and eventually export commercial fusion reactors. But there's more. Japan's strategy includes building strong international partnerships, especially with European organizations, through frameworks like the broader approach. These partnerships help with the exchange of technology and knowledge and are vital for training the next generation of fusion specialists. Preparing these experts, along with the necessary materials and technologies, is crucial for the success of future reactors. Japan is vigorously advancing its efforts in scientific exploration and industrial growth to become a leader in the upcoming wave of energy technologies. Their ambitious strategy reflects a strong commitment to positioning themselves at the forefront of the global energy sector. They are eager to tackle significant technological hurdles to transform fusion into a revolutionary power source. Adding to the excitement, Shai, a pivotal figure in the fusion energy arena, is exhilarated by these advancements. The recent surge of innovative concepts and financial investments from private sectors into fusion energy is encouraging. Shai is optimistic about the increasing participation, which indicates a widespread recognition of fusion energy's capacity to revolutionize our power generation methods, steering us towards a cleaner and more sustainable future. Could the pursuit of nuclear fusion create unforeseen environmental or safety risks that outweigh its benefits? Share your thoughts in the comments below. Hit like and subscribe for more insightful discussions.